Good afternoon, everybody. I hope I'm audible. This is the third lecture
Yes,
in
ma'am,
the
you are.
series. Okay. This is a third lecture in the series, which is on basic reactor physics concepts. Again, I would like to recap what we have done in the past lecture. What we did last week on Friday was the types of neutron interactions. We saw how neutrons are used as projectiles and the reactions take place. And then we also saw some charged particle reactions. And we also saw how neutrons are being produced in some of these reactions. I had also mentioned to you that some of these types of reactions are threshold reactions, which happens only at certain energies and beyond. Then I gave you the distinction between fissile and fertile nuclides. I gave you the cross-section profiles, and I mentioned to you what is the nature of fissile and nature of fertile and how do they behave. We also talked about the energy dependence of cross-section. Basically, we talked about how the cross-section varies as a function of neutron energy. I had mentioned to you that there are three distinct regions. The thermal region almost ranges from 10 to the power of -5 electron volts to about 10 electron volts. Then there is a middle region, which is the resonance region, which is characterized by sharp resonance peaks where the interaction cross-section is very, very high. And this ranges from about 10 eV to about thousands of keV and so on. And then there is a distinct fast region where the cross-sections are very, very low. And also I had mentioned to you or impressed upon you that with the temperature of the medium, the cross-sections would vary because the temperature of the neutron would vary, and therefore the neutron nucleus interaction mechanism would vary, would change. So what is the effect of temperature of on the cross-sections? For example, the fission cross-section or the capture cross-section or the scattering cross-section. And I also mentioned to you that there is, because of the increase in temperature, you have something called as a Doppler broadening, which is very useful in some of the reactor characteristics. Then we saw about what are the types of reactions for neutron detection. I was talking to you about helium-filled gas detectors and the boron N-alpha reaction, which is generally used for neutron detection. I gave you the cross-section as a function of energy. My lecture notes will be probably uploaded today so that you can see all these things. Then we also saw about what is the energy of the spectrum of the neutron or spectrum of the thermal neutrons. I told they mostly follow the Maxwell-Boltzmann distribution, so they are called as the Maxwellian energy spectrum. Then we emphasized what is the capture to fission ratio, how it is important for a reactor design or to characterize the materials. And we also talked about the parameter eta, which is characterized by the number of neutron produced per fission per neutron absorbed. Then we also talked about nu, which is actually the number of neutrons produced in any fission reaction, which is called as a neutron yield of a fission reaction. And we saw that the capture to fission ratio is changing in the thermal energy region and in the fast energy region. And for certain isotopes, if capture is less, you would have more fissions. So uranium-233 thermal fission is very useful in that matter, in this, because its capture is very less. Whereas plutonium is useful in fast energy regions or fast spectrums. Then I was asked in my table, what is the difference between the cross-section and also how epithermal cross-section, that is the resonance integrals, which is the total reactions or total cross-section averaged energy, which is given as resonance integrals in the energy range, in the resonance energy regions. So this last lecture was mostly on the type of interactions and the energy behavior, neutron energy behavior of cross-section with respect to the neutron energy. Today, what we will talk is a little more about reactor physics. See, I had already mentioned to you that you would not have learned reactor physics in your college because it's a takeoff from the neutron nuclear physics, and then we have to say how the neutron is being multiplied in a chain reacting system and how it is being controlled and how it is it is being produced. So today we'll be talking about neutron multiplication. I will talk about the neutron life cycle. We will talk something about the neutron generation time. And also there is a simple formula which is governing this neutron multiplication in a chain reacting system. So we call this as a 4-factor formula. I will introduce to you this formula and also talk about what is a finite system versus infinite system and how the neutron diffusion takes place and what is the law governing the diffusion of neutrons and some concepts about neutron leakage. When I'm mentioning this, there is also important, I have to mention something about the slowing down of neutrons, how neutrons are losing energy and why we, for example, for a thermal reactor, why we use hydrogenous material or whether we use beryllium or carbon or graphite, how the properties change and how the neutron interactions will change or the energy lost by collision with the moderating atoms would change. So some brief concepts on slowing down and what is the energy decrement on a collision. And I will introduce a concept of lethargy. And when we're talking about neutrons, thermal neutrons, I will introduce the concept of diffusion length. And as I will leave you with some basic reactor design concepts for different types of reactors. So first, let us talk about what is meant by criticality. I had already mentioned to you that a nuclear reactor is one in which neutrons are produced, sustained, and controlled. So each of these things which I have given in red is very, very important. So you can see that the neutrons have to be produced. So here I'm schematically showing that uranium-235 atom is bombarded by a neutron and it gives you 2 fission products and 200 MeV of energy, and these around 2 to 3 neutrons on an average. These neutrons further cause fission in further uranium-235 nucleus. Some of them will get radiatively captured and become uranium-236 and so on. So here you can see a chain reaction, which is a propagating chain reaction. So the neutron is acting as a chain carrier. So because these neutrons are acting as a chain carrier, we need to account for these neutrons and we need to see what happens to these neutrons in a medium. Suppose we talk about a neutron which is born in one generation and suppose this is another generation. So what is the number of neutrons which have crossed from one generation to another generation? So we can define a multiplication factor for this medium. We'll be talking more about this multiplication factor. It's nothing but neutron multiplication. So it's I can say that it's a number of neutrons in one generation to the number of neutrons in the preceding generation. Or if you want to talk with respect to the production and loss mechanisms, we can say it is the rate of neutron production, which is because of the fission. And if there are any other sources also, sources of neutrons in a medium, then it is the source and fission. And the rate of neutron loss to the rate of neutron loss. The ratio of neutron production to neutron loss, the loss from the system can be taking place by absorption, for example, I told you, which is captured in uranium-235, or leakage from the system. You consider a physical system, which is basically like a nuclear reactor, a finite system. So there could be some neutrons which are leaking out of this. So the loss mechanisms are governed by both absorption or capture, radiative capture, and non-fissile capture, we call it, and also by the loss from the neutron due to loss from the system due to leakage. So this ratio is what determines the multiplication factor or how the neutron propagates in a chain reacting system. I'll come to this formula a little later. Right now, this is what is a 4-factor formula. Since we are talking about infinite system, that is, I'm talking about chain reacting system, which is infinitely in volume and so on. So we call this as an infinite multiplication factor or K infinity. Now, if for a finite system, it would be little different, which I will talk to you a little later. But right now you understand that the neutrons are getting multiplied in the reactor or in the chain reacting system, and we have to account for the neutron. If this factor K is equal to 1, that is, if production is balancing the absorptions and the leakage or the losses, then you have what is called as criticality, or the neutron multiplication is invariant with time. The neutron's density is going to not change with respect to time, or your K, when K is equal to 1, your production is equal to your loss, and thereby you can maintain a chain reaction in a reactor. So that is what is meant by sustained or maintained. So then we say this nuclear reactor to be in a dynamic equilibrium. See, it's all these processes are happening. There is capture happening, there is fission happening, there is transmutation happening, there is scattering happening. There are so many reactions which are happening. There is losses, there is absorptions, and so on, and leakages. So this nuclear reactor can be considered to be a dynamic equilibrium, which is maintained between this production and the loss mechanisms. Okay, so here there's pictorially I have given you this. I will explain a little more about this. Consider one initial fission neutron in this figure, which is causing fission in uranium-235 nucleus. Out of that, some fast neutrons will be produced, and these fast neutrons could again cause fission in some of the, because fast cross sections are also existing, which I was explaining to you when I'm talking about cross sections. And further, what is happening is these neutrons get slowed down to KeV regions. That is because of the interactions with the nuclei of the medium, like moderator or uranium-235 and so on. And though they come into resonance energy regions, and they will get resonantly captured, where there is a lot of peaks which we saw. And some of these are non-fissile captures, then the neutron is lost from the system. And if it's this fissile capture, then we get some absorption in the fuel, and then these neutrons are becoming again thermal, because on further collisions with the moderating nuclei, and there they'll become thermal neutron and again cause thermal fission in uranium-235. So this is called as a neutron life cycle, and each is characterized by these 4 factors which I'm trying to tell you. So one fission neutron which is being absorbed by uranium-235 nucleus gives you new fission neutrons at the end of when it is causing fission. So this is what is the neutron life cycle, which we are going to talk about in a little more detail. First, let us talk about the neutrons generated in fission. I had already mentioned that any fission events emits new neutrons. This new is called as a neutron yield at the instant of fission, due to fission from all energies. Okay, but not all neutrons are participating in a fission reaction. Some of them get captured. Like I told you, uranium-235 has 100 bonds as capture cross-section and 580 bonds as fission cross-section. And so there is something called as a capture to fission ratio or fission cross-section, which is defined by a quantity called alpha, and that alpha is given by sigma C by sigma A. In uranium-235, it will be 100 by 680, in simple terms, for one particular neutron energy. So in order to continue the fission process, the neutrons must be produced effectively. So this is termed as a regenerative factor eta. This eta is different from the nu. Eta is defined as a number of neutrons which are produced per thermal neutron absorbed. Any fission event is giving you new neutrons. Let's say all neutrons of all energies are giving you new neutrons, but we need to find out how many thermal fissions, how many thermal neutrons have absorbed, which is giving you the neutrons. So that is given by a factor E, which can be easily expressed as nu sigma F by sigma A. Nu into sigma F is basically fission yield and fission cross section, and sigma A is the thermal absorption cross section. So this ratio is called as a regenerative factor, or eta, which is the most important for reactor design. So this sigma A can also be written as sigma F if we consider absorption to be only consisting of fission and radiative capture. So it can be considered to be sigma F plus sigma C in the denominator. So this eta will reduce to nu by 1 plus alpha, where alpha is actually, I have told you, as sigma C by sigma A. So you have to understand there are two distinct neutron numbers here. Basically, one is a neutron yield, which is number of neutrons emitted in a fission event due to fission from all energies. And then there is a regenerative factor eta, which is defined as the number of neutrons produced per thermal neutron absorbed. Okay, so now we were talking about this neutron chain reaction or neutron multiplicity. So let us start with n thermal neutrons in a chain reacting system. Let us assume a volume which is consisting of fuel and moderator, and let us start with n thermal neutrons, which is the figure which I was showing you. Of these n neutrons, they can cause fission in uranium-235. They produce n into eta fast neutrons. This is what we saw, that eta is a regenerative factor. And so if we have started with n neutrons, after fission, I will get n eta fast neutrons. Now, these neutrons are of the energy range MeV, which I had already explained in the first lecture, that fission neutrons having a peak at 2 MeV. And they're ranging from about 0 to 10 MeV. So these neutrons can get captured in uranium-238 atoms. We already saw that uranium-238 has a good threshold for fast fission, for neutrons of fast energy. So the critical energy, that much critical energy is available by these fast n eta fast neutrons, so they can cause fission in uranium-238 atoms. When they cause the fission in uranium-238, you're going to get more number of neutrons. So this is defined by a factor epsilon. So these neutrons have to cross this fission threshold of uranium-238 and have to be come down to resonance energy regions and thermal energy regions for further slowing down. So if epsilon is defined as the fast fission factor, now we have, after these neutrons have crossed the fast fission threshold of uranium-238, I am just considering a simple system which is having only U-235 and U-238, just to understand the concept of what exactly happens in a nuclear chain reacting system. So we started with n neutrons, we got n eta fast neutrons, and after they have crossed the uranium-238 fast fission threshold, we have n eta epsilon fast neutrons, which are now available for further slowing down. Now, I had already mentioned to you that in the kilo electron volt regions, uranium-235 and uranium-238 exhibit a lot of resonances. So these resonances will capture the neutrons. So the neutrons have to escape these resonances and come down to thermal energies. See, absorption of neutrons in these resonances, resonance energy regions or resonance peaks, will reduce the number of neutrons. Whereas if it's a fission resonance, it will tend to increase the number of neutrons. So that is why I said the cross sections are very, very important. We need to know what type of reaction is happening with what type of energy of the neutron. So now we have n eta epsilon fast neutrons, which have coming down to resonance energy regions, and they're getting captured in the resonances. So a factor P is used to represent the escape of neutrons from these resonance energies. I have already told you that they have to escape these new resonances if it's a capture resonance, and then come to the energies at electron volt region to get slowed down further. So thus now we have eta epsilon P, n eta epsilon P neutrons which have escaped the resonances and are available in thermal energy regions. So now this many thermal neutrons are available. I have not colored it in red. It's my mistake, but anyway, you can see that we started with n neutrons, then we got n eta fast neutrons, then we got n eta epsilon fast neutrons which have crossed the uranium-238 fission threshold, and now after it has crossed the resonances, we have n eta epsilon P, thermal neutrons, which have crossed after K regions and come down to thermal energies. Basically what we are trying to do is we are trying to follow the life cycle of a neutron. What happens when it is neutron is born in fission to when it is going to get captured the next generation in the next uranium-235 nucleus. Now these thermal neutrons, I told you there is in a chain reacting system, you could have fuel, you could have coolant, you could have moderator and other structural materials. So not all these thermal neutrons are going to get captured by the fuel. Only some of them will get captured. Only a portion of them, a proportion of them will be getting captured by the fuel. So a factor F is defined, which signifies the effective utilization in a fuel. So this is the fuel utilization factor or thermal utilization factor. Are absorbed by the fuel to cause further fissions. So now we have eta epsilon PF neutrons which are available for causing fission in a uranium-235 atom. So the K infinity multiplication factor for an infinite homogeneous system can be defined as neutrons produced in one generation, which is nothing but n eta epsilon PF neutrons have been produced, to the divided by the neutrons absorbed in the preceding generation, which is n. We started with n neutrons. So this is what is the four-factor formula, which is eta epsilon PF. So the K infinity, that is the multiplication factor for an infinite system, is defined as eta epsilon PF. Now, if you see my slide on the neutron life cycle, you will understand what are all the various processes which has happened during the neutron when it has got absorbed as a fast neutron, produced as a fast neutron, and then finally got absorbed as a thermal neutron. So what are the definition? Once again, we'll see the definition of the four factors. Eta is nothing but nu sigma f by sigma a, which is the regeneration factor, and it is defined as a net neutrons produced per thermal neutron absorbed. Here, if you have noticed, I have gone to the macroscopic cross section because I have multiplied by the number density or nuclear density of the fuel atom or of the medium. And epsilon is the ratio of the number of neutrons produced by fissions, both thermal and fast, to the number of neutrons produced by thermal neutrons only. P is a resonance escape probability. It's a probability. So it depends upon the cross sections and so on. And F is defined as the thermal neutrons absorbed in fuel to thermal neutrons absorbed in total thermal neutrons absorbed. We can see it as, I already told you, sigma into phi is the reaction rate. So let us say sigma F into sigma AF into phi F into VF is the total number of fission reactions which have taken place in the fuel, and in the denominator I have the total absorptions in the fuel. In the moderator, M stands for moderator and P stands for, let's say, other structural materials, poisons and so on. So the denominator is the total absorption which is happening in the medium, and this is only in the fuel. So this ratio is called as the thermal utilization factor, F. So now we have seen that the four-factor formula for a neutron multiplication system, multiplying system or chain reacting system, which is for an infinite system, it is defined by the four factors, which is eta epsilon PF. But I had already told you that in reality, the system is not going to be infinite. It is going to be finite. Again, excuse me for my spelling mistake here. Finite like in a reactor. So there will be leakage of neutrons out of the system. So the effective neutrons that are characterized by the effective neutrons which are there in the system or in the medium is being characterized by a non-leakage probability. So this probability depends upon the geometry of the system, whether it is how small or how large is the volume of the system. So effectively the neutrons are not going out of the system. So for this finite system, we have something called as an effective multiplication factor, K effective. Right now you assume it to be simply that it is K infinity multiplied by the non-leakage probability. We'll come to the expressions of all these things a little later. So for the finite system, you have a K effective or effective multiplication factor, which is different from the infinite multiplication factor, which I was describing to you so far. Again, we have already assumed that the system to be a homogeneous mixture of fuel and moderator and so on. But in reality, it's not going to be like that. See, this is, for example, I have drawn a fuel rod in a moderating medium. And this is a homogeneous mixture of both fuel and moderator. Now, each of these factors are going to be different in this system and this system. So this is a typical heterogeneous arrangement like a fuel pin and its surrounding moderator. So I have given you the various factors, how they will change. See, since eta is a property of the material, it is a property of the uranium-235 nucleus or the natural uranium, whatever you're using. So it is not going to change whether you're here or whether it is here. It's more or less similar. Now, epsilon is a property of the how the fast neutrons encounter the fuel in the vicinity. So if fast neutrons are produced here, it is available here in the fuel pin itself, and so it will cause more fissions. So in a heterogeneous system of fuel and moderator and a fuel pin, epsilon heterogeneous will be slightly larger than the homogeneous medium epsilon. Similarly, p heterogeneous, again the resonance neutrons are born here in the moderator because it will get slowed down here, and there will be more probability for the neutron to get available, to get absorbed in the fuel rod, and so therefore p heterogeneous is also going to be larger than p homogeneous. Now consider the thermal utilization factor. In a thermal utilization factor, what is happening is that here, when in a homogeneous system, you have fuel and moderator mixed up in a homogeneous mixture. So you will find the moderator atoms everywhere and the fuel atoms everywhere. But whereas here, you have moderator atoms in a specific region and fuel atoms in a specific region in the center of the volume. And so F heterogeneous is going to be lower than F homogeneous. So in a finite system, you will see that K infinity heterogeneous is, this should be homogeneous, is greater than K infinity homogeneous. Or basically, how do you increase K infinity? You can increase K infinity by suitable reactor design. That is why you will find that the fuel is in the form of a rods, or the fuel is in the form of a cluster, or fuel is in the form of a box, or different arrangements of fuel is there. We'll come to that a little later on, but right now you just try to understand there could be differences in the homogeneous and heterogeneous systems. Now I am giving you some design parameters which just to show you, impress upon you that why certain materials are required and why certain materials will not give a proper critical arrangement. I was always insisting upon the ratio of moderator to fuel. The fuel to moderator atoms we always consider. So here I have plotted a curve of K infinity versus fuel to moderator ratio, Nm by Nf. That is moderator to fuel ratio. There is a definite peak for any reactor design. You can have a definite peak and it reduces. So for this particular arrangement of moderator to fuel, I will have maximum K infinity. So we see that in an operating conditions, we try to design the system almost in and around the peak. So that's why we will be optimizing the geometry of the fuel pin, we'll be optimizing the amount of moderator, everything. So here I have given you some of the most important factors, which is the P and F. F is a thermal utilization factor and P is the resonance escape probability. Some design parameters for a natural uranium fuel with different moderators. The common moderators which we use are water, heavy water, beryllium and graphite. And this is the number density ratio of the number density of the fuel and moderator. And here you can see that K infinity should be greater than 1. Only then you will have a chain reacting system. Otherwise, it will be dying down. The chain reaction will be dying down. So you can get a critical combination only with heavy water in a natural uranium system. So natural uranium can become critical only with heavy water, where you can see we get a K infinity of about 1.145. All others are lower than 1, so they will not form a critical arrangement. I have already mentioned to you that if we consider a natural uranium fuel, then eta and epsilon are properties of the materials. They're not going to change. So by making it heterogeneous, we can increase the K infinity, which is what we saw in the last slide. And here we have seen how by making it heterogeneous, both P and F are acting in opposite directions. F reduces and P increases. So thereby, by proper combination of the fuel to moderator ratio or the fuel sizes and the fuel pin sizes, we'll be able to address this and make the K infinity as high as possible. So far we were talking about the chain reacting system, where we didn't consider anything about the energy of the neutron, but basically we said that they are slowing down and it was a one-dimensional kind of a system. But let us now, most important thing which is happening in a nuclear reactor for neutrons is the diffusion of the neutrons in a medium. So let us give some attention to diffusion of neutrons. Here I have tried to plot just give a graphical representation of how the neutron could vary, could change its position and path in a medium. So it is diffusing. So it could have an interaction with a nucleus here, and it goes in this way. Then it would have another interaction, and it goes this way, and so on. And so this is some sort of a Brownian motion. And this R would be the crow flight distance for a neutron which started from here and ended up here. So this neutron diffusion is governed by a fixed law. This is the fixed law as applied to the gases and liquids, which you must have studied in your MSc. So when the neutrons are in thermal equilibrium with the moderator, they diffuse following a Brownian motion. Now, in analogy with the fixed law, we have this neutron current. This J is the symbol for neutron current density. It is proportional to grad phi, or the proportionality constant is D, which is the diffusion coefficient. So J is proportional to the gradient of the scalar flux. This is a scalar flux. So we say the gradient of the scalar flux. Phi is a neutron flux, and it is defined as the number of neutrons flowing or crossing per unit area per second. It is represented as number per centimeter square per second. That is this phi here. Now here you can obviously see the difference between phi and J. Phi is the scalar quantity and J is the neutron current density, and it has a particular direction. And this D is a diffusion coefficient. It is not exactly a proportionality constant. It has some it has the dimensions of centimeter or some of length, which will come to a little later. But this is called as a diffusion coefficient, or this is the property of the medium for the neutrons to diffuse, or how effective is the medium for diffusion of the neutrons. Now this fixed law has been derived as considering so many assumptions. First is the medium is homogeneous. The medium monoenergetic neutrons are diffusing in this pattern here. The flux is a slowly varying function of the medium, and there are no other strong absorbers of strong sources of neutrons present in the medium. So if you assume all these things, you can get a simple formula for the neutron current density. So the net flow of neutrons across a surface is called as a neutron current density, and it is defined as N into V. V is a velocity. If you have the correct, because we take direction into account, I have put the variable omega here. So neutron density is a function of both R and omega, and then if you multiply it by the velocity, you get the current density. This and you integrate it over the energy over the angle, you get the current density. This N into V can be seen as the neutron flux. Flux is nothing but N into V, and J is nothing but the neutron current density. I hope you have got the difference between J and phi. Now let me introduce some concepts of neutrons slowing down, because this is also important if I have to continue the arguments for the rest of the lectures and so on. We consider this kinematics to be a two-body kinematics. This neutron is interacting with a nucleus. A neutron is hitting the nucleus, and then the neutron goes in this direction, the nucleus goes in this direction, and neutron goes in this direction. So if they have the velocity v1 in the beginning, then what happens? The velocity of the neutron is v2 after it has collided. Then you consider the center of mass frame, and it's a simple two-body kinematics, which is a neutron, just like a two-body collision. And then you get the final velocities and the initial minus final velocity, which is dependent upon the mass number, which is A of the nucleus. What I want to understand, what I want you to understand more is that, let us say this neutron is born as a fast neutron at the instant of fission. Now it has to be slowed down to get into become to thermal energies to cause thermal fissions. So if E1 is the energy of MeV, so you can see that at each collision it loses some energy. And finally, I have tried to plot this neutron energy scale. And finally, we have this neutron as a thermal neutron, which could cause fission. Now, the energy lost in one particular, these are all elastic scattering. So the energy lost in one particular, in one scattering event is characterized by this quantity alpha, which is nothing but A minus 1 the whole square by A plus 1. A is already the mass number of the nucleus. Now the ratio of the loss of energy, that is E2 minus E1, is given by this particular formula, which can be derived. I don't want to go into all those things, but I just want you to understand that on an average, in one particular collision, the energy, the lost is proportional to alpha. So the minimum loss of energy is there when at an angle of, that is a direct interaction, theta is equal to 0. So maximum Emax will be equal to E1. There will be no loss. There is no loss in energy. And the maximum loss of energy will be when theta is equal to pi. And E minimum, that is the energy lost, would be equal to alpha into E1. The minimum value of energy to which a neutron can be reduced by elastic scattering is given by alpha E1. That's what a single scattering event will reduce a neutron energy from E1 to alpha into E1. That is depending upon the size of the nucleus, which is characterized by this alpha, which is the mass number of the nucleus. So the fractional loss of energy in one collision is given by E1 minus E minimum by E1, which is given by the factor 1 minus alpha. Actual maximum loss of energy in a collision is E1 into 1 minus alpha. Here I just want you to give some examples, because in the next argument, in the next slide, I'll be telling you what exactly happens when neutrons are colliding with hydrogen, or when neutrons are colliding with the beryllium, and so on. So you can see that for hydrogen, A is equal to 1. So alpha is equal to 0. So it means that a neutron can lose all of its energy in just one collision with hydrogen. That is what it's a low mass number nuclei. For carbon, A is equal to 12. Alpha comes out to be 0.716. The maximum fractional loss of energy, of neutron energy with a carbon atom would be 1 minus 0.716, which is around 0.284. It's a fraction of loss. Now, since this energy scale is varying from MeV to electron volts, this is a large scale, big, spanning several decades. So what is happening is that it is convenient to express this energy of neutrons in a logarithmic form, which is a dimensionless quantity. Suppose I define a factor U, which is log of E naught by E. This is initial energy, this is the final energy. Where E naught is the maximum energy of the neutron, so that U is always positive. So as the energy of the neutron increases, the lethargy, energy decreases, the lethargy will increase. So it's lethargic. That means it is lethargic or to the slowing down. So the slowing down process is considered to be a lethargic, or how the neutrons is losing energy. And so we define a quantity which is dimensionless, which is called as a lethargy of the neutron. It is convenient in some reactor physics parlance to express the neutron energy loss in the form of lethargy. That is why we say this. Now, if U1 is corresponding to energy E1, a lethargy of U1 corresponds to energy E1, the energy of the neutron before collision. And if U2 corresponds to the energy E2 after collision, then delta U is a change in lethargy, which is given by log of E1 by E2. It's simple. From this formula only I have written this. Now we define another quantity, which is the average change in lethargy per collision. This is defined by a number, by a parameter zeta. We define this as an average change in lethargy per collision, and because each collision is losing, the neutron is losing energy, so we are quantifying it by this average energy decrement, and 1 by zeta will be the average number of collisions per unit lethargy change. So this is what is going to define my how to use which moderator. 1 by zeta is the average number of collisions per unit lethargy change. So you can understand lethargy in a much more better way if this is the energy of the different xi, and this is the energy of the neutron, and this is how the energy changes. This E is equal to E naught into e to the power of minus u, and this interval is called as the zeta. That is the energy lethargy change per unit collision, per collision. Lethargy change per collision. So 1 by zeta is the average number of collisions per unit lethargy change. This is regardless of its energy of its energy. A neutron must have, on an average, the same number of collisions in a given medium to increase its lethargy by a specified amount. Suppose in a uranium and a water system, I want the neutron to get lethargy to reduce by certain amount. Then the number of collisions required would be defined by this zeta. So neutron on average loses more energy initially than towards the end. This I will not discuss much, but because this average, because these are all the scattering collisions are all statistical kind of a phenomenon. So you have something called an average decrease in the natural logarithm, and that is called as average logarithmic energy decrement, and it is defined as zeta is equal to 1 by, it can be derived 1 by 1 plus alpha by 1 minus alpha into log alpha. So you can see that it is independent of the initial energy. I just want you to understand that as A increases, the zeta decreases. Now here you will appreciate this more with this table here. The average number of collisions with a particular moderator nuclei to decrease, let us say from 2 MeV to 1 eV, is given by this log of 2 into 10 to the power of 6 by zeta, which is nothing but 14.5 by zeta. Now you can see for different elements I have given you. For hydrogen, mass number is 1, alpha is 0. So only 15 collisions are required for the neutron to go from 2 MeV to 1 eV. For deuterium, it is about 20 collisions. Now you can see that for carbon, it is about 92 collisions are required if a neutron, when it is striking a carbon atom or graphite moderator, let us say if we have a graphite moderator, to go from 2 MeV to 1 electron volt. And for uranium, it requires about 1700 collisions, because its A is very high and alpha is very high, and zeta is so, therefore is going to be very, very small. So this will decide what kind of system I would use, or what kind of moderator is required, or what kind of a coolant is required, and which fuel is required. But basically I want you to understand the energy is lost in a scattering collision. It is an elastic collision, and continuously it is neutron is losing energy when it is in a chain reacting system, and thereby we have defined a term lethargy, which is a dimensionless quantity which is depending upon the logarithmic decrement of the energy. Then we defined a quantity average logarithmic energy decrement as zeta, and we also found out how many collisions are required for the neutron to lose energy from MeV to say EV region. Now, while discussing the neutrons, I was also mentioning to you that the thermal neutrons follow Maxwell-Boltzmann distribution. Here I have just given you a simple calculation. The Maxwell-Boltzmann distribution is somewhat like this. I have just tried to plot it by hand, so it is not perfect. So you can see the neutron energy is varying from 0 eV, 50 eV to 250 electron volts. And I do a small mathematics here, taking the mass of the neutron, and the energy of the thermal neutron is nothing but half mv square. If you do all these mathematics, you can say that at 300 Kelvin temperature, the velocity of the neutron would be 2220 meters per second. Yesterday in my table, you would have always seen that The thermal neutron energy is 0.0253 electron volts. I have corresponding velocity is, I have told you, it is 2200 meters per second. And from Maxwell Boltzmann distribution, you know that is the most probable velocity or energy of the neutron, which is given by Vp is equal to root of 2 kT by m. Now we were talking about so many things about moderation, moderator efficacy, and the number of collisions required and all. Here I am giving you two examples of two different reactors. This is a boiling water reactor, which is light water, and this is a heavy water reactor, which is our Kannan pressurized heavy water reactor. Now here I have given you the various moderating properties and criticality property. Also I have given you, which is K infinity. Suppose I have a moderating medium, light water. The xi sigma s, this xi sigma s, that is the zeta into sigma s, is something called as the moderating power of a medium. So these are all dependent upon the cross sections, which is at thermal energies and so on, and you can easily calculate them. For one particular energy I have calculated, which is the 2200 meters per second cross section, and I get a number of 1.28. Similarly, we define another thing. This alone is not sufficient to say which is a good moderator. We require something called as a moderating ratio, which is given by the formula xi sigma s by sigma a. So this is called as a moderating ratio. And here you can see that for heavy water, the moderating ratio is very, very high. So I would like to, we would like to use heavy water as moderator for thermal systems. Then there is something called as a slowing down length. I told you the neutrons are continuously losing energy. So we are defining a diffusion coefficient and a diffusion length. So this is something like this concept is a little difficult to understand, but I'll tell you a little later on. But just now you just take it as numbers. This is slowing down length. That is in 5.2 centimeters in heavy water, in light water, the neutrons will get slowed down to thermal energies. Whereas in heavy water, it requires about 11.4 centimeters and so on. And this diffusion length also I will come to. Right now you consider, you understand it to be the length traveled by a neutron in a diffusing medium, which is characterized by the diffusion coefficient and which is given by these numbers here. So here you can see that D2 is the best moderator having the highest moderating ratio. So these are all for natural uranium again. So, and the natural uranium can become, this I have already mentioned to you, can achieve a critical combination with D2O moderator, whereas it would not be possible with the other moderating systems like light water or beryllium or graphite. So here you can see that in a light water, the fuel rods have to be placed close to each other because the diffusion length is only 2.7 centimeters. If I place it more further, then the neutrons will get lost and effectively it will not get absorbed by the fuel. Whereas in a heavy water, this is one fuel assembly, the other fuel assembly is somewhere here. So you can see there is a distance between one fuel assembly and another fuel assembly. There should be enough heavy water for it to get moderated and the neutrons to reach thermal energies to cause a fission in the next fuel assembly. So in a light water system, the spins are placed closer, whereas in a heavy water system, the moderator quantity is larger. So you will find that light water systems are compact and small, and heavy water systems are huge, bigger. There is one more example which I'm trying to graphically show. This again I have picked up from some of the presentations. Here you can see that this is the fuel rod, and here you can see this is the water as coolant, and water is going from top to bottom. Let us say water is acting both as coolant and moderator. So the neutron is getting causes an collision in this fuel rod, then it gets slowed down by the moderator here or the coolant here and causes collision in the next fuel rod and so on. So the fuel rods are spaced like this. Whereas in a heavy water lattice, heavy water reactor, you can say this is one fuel assembly. This is, I have taken 540 megawatt electric PHWR, which is a 37 element assembly. I'll come to these things a little later. and this is two assemblies are separated by a distance of about around 20 centimeters or so, because only then I will be having effective moderation. Because I have used light water, here I would have to use enriched uranium system. We'll come to that also a little later. Here we have used natural uranium, and that is why we have gone for heavy water lattices. What I wanted to understand is that there are different types of moderator, there are different types of moderator characteristics, and there is different types of interactions which are taking place. And so the reactor design involves all these concepts. So today I think it's a little heavy. Reactor physics was introduced to you. For the non-starters, maybe a little difficult to understand, but I have tried to make it as simple as possible. So in summary, what we have seen today is how neutron multiplies in a chain reacting system. So we have derived the four-factor formula. We have also seen how to account for the neutron transport in a chain reacting system. And we saw about neutron diffusion. Then we saw that the law which is governing the neutron diffusion is fixed law, which is as applied to the gases and liquids. We first saw about a non-multiplying medium. Then we derived what is current and what is flux. Then we got some insight into the homogeneous and heterogeneous system. We saw what is a neutron slowing down phenomena, how the neutron is losing energy with successive collisions. And then we defined two terms. One is the lethargy and one other is the average logarithmic energy decrement. If you go through my presentation, I think you will understand all these things. I will leave today's presentation also. It will be shortly uploaded. Then we saw what is the energy distribution and what is the most probable velocity of the thermal neutron. And we also saw some design parameters for common moderators, and how we also saw that natural uranium and heavy water is a combination which can give you a critical current combination, which can make the reactor critical. We also saw what is criticality, what you understood by criticality, that there is a perfect balance between the production mechanisms and the loss mechanisms. So tomorrow I will be starting, or in the next class I would be starting with this balance equation, which we will be trying to develop for a simple system. So I hope it is clear today. I stop with this.